Right now, light that began its journey more than 13 billion years ago is slipping quietly into our telescopes. It comes from an object so small and so faint that most of humanity has no idea it exists. Yet, the James Webb Space Telescope has just confirmed something astonishing. This tiny patch of ancient starlight hides a cosmic giant, a supermassive black hole living inside a galaxy no larger than a cosmic ember. Its name is Canucks LRDZ 8.6, a minuscule galaxy from the universe's first dawn. And its central black hole is growing faster than any theory says it should. Faster than physics predicted. Faster than galaxies were supposed to allow. Tonight, we will uncover how this galaxy formed so early, why its black hole is far too massive for its age, and what this discovery reveals about the first moments of cosmic structure. If you enjoy journeys that reshape your sense of reality, hit like and subscribe. Let's begin. We begin with the strange fact that Canucks LRD Z8.6 was not discovered through direct observation. It was revealed only because a massive galaxy cluster acted like a gravitational mirror. Without that distortion of space-time, this galaxy would still be unknown. When astronomers first pointed the James Webb Space Telescope toward a distant region of the sky, they were not expecting to find a tiny, ancient galaxy tucked behind millions of times more mass than itself. The cluster in front of it was enormous, containing thousands of galaxies bound together by gravity, sinkholes of dark matter, and oceans of hot plasma stretching for millions of light years. This cluster was so heavy that it bent the space around it, curving the paths of passing photons like a lens carved out of space-time itself. For most of cosmic history, that warped region acted like a barrier, hiding anything behind it from view. Only with JWST's sensitivity could astronomers see that this wall of gravity was not a barrier at all. It was a window. Gravitational lensing is one of the strangest predictions of Einstein's theory of relativity. It tells us that anything with mass, whether a star or a galaxy cluster, reshapes the space around it. Light does not curve because the light changes. It curves because the space it travels through is warped. When that warping becomes extreme, regions behind the mass are stretched, brightened, or even duplicated. In the case of Canucks LRD Z8.6, the galaxy cluster in front of it magnified the faint object by several times, brightening a signal that otherwise would have remained buried beneath the glow of the universe. This phenomenon is not rare, but the alignment required to reveal a galaxy as small and distant as Canucks LRD Z8.6 is incredibly precise. The galaxy had to sit at exactly the right angle, behind exactly the right mass, at exactly the right distance. If the alignment were off by even a fraction, the light would have been smeared or lost entirely. The fact that it wasn't suggests the universe occasionally leaves small clues for anyone patient enough to look. In this case, it left behind a magnified fingerprint of a galaxy from the cosmic dawn. As astronomers studied the distorted arc of light produced by the lensing effect, they realized something even more remarkable. The image was stretched, but not destroyed. The spectral signature remained intact. Each wavelength carried information about the galaxy's stars, gas, and motion. The gravitational lens did not erase the data. It amplified it. It was as if the universe itself had decided to lend its own telescope for a moment, allowing us to peer past the walls that normally limit our vision. Behind that wall of gravity sits one of the earliest and smallest galaxies ever recorded. A galaxy that would have vanished without the lensing effect. A galaxy carrying the light of an era where the first structures were still assembling. And at its center, as astronomers would later discover, waited for something far more massive than anyone expected. If not for this cosmic lens, the story of Canucks LRD Z8.6 would never have reached us at all. JWST's infrared instruments were built to capture the faintest thermal whispers from the early cosmos. Canucks LRD Z8.6 sits so far away that only JWST's extreme sensitivity allowed its ancient light to be separated from cosmic noise. Detecting a galaxy like this is not as simple as pointing a telescope and taking a picture. At such extreme distances, light becomes fragile. It is stretched by the expansion of the universe, dimmed by time, and buried beneath infrared background glow from stars, dust, and even the telescope itself. Every observation becomes a hunt for meaning inside a sea of noise. In that environment, ancient galaxies often disappear entirely, leaving no distinguishable trace. But JWST was designed for exactly this challenge. With its cold, shadowed mirror and ultra-sensitive detectors, it can reach into wavelengths where the first galaxies shine brightest. Infrared light is the currency of the early universe. As light travels across billions of years, it stretches into longer and redder wavelengths. The most ancient galaxies no longer radiate invisible colors. Their light has drifted deep into the infrared, invisible to human eyes and opaque to older telescopes. JWST was built to intercept this stretched light, using detectors cooled to near absolute zero, so they produce almost no thermal noise of their own. When its instruments focus on a distant region, the telescope becomes a still, quiet ear, listening for signals that have crossed nearly the entire age of the universe. The detection of Canucks LRD Z 8.6 came from painstaking work. Astronomers collected long exposures, stacking them to amplify the faintest glimmers. Every pixel was inspected, filtered, and analyzed. Data from multiple wavelengths was combined to confirm that the signal was not a cosmic ray, not a glitch, not a passing artifact, but something real. The techniques used were so sensitive that they can detect the heat from a single faint galaxy across cosmic time as easily as one might detect a candle flickering on a shoreline miles away. JWST's spectrographs played a key role as well. Instead of simply recording brightness, they split the light into its constituent wavelengths. This revealed patterns that confirmed the galaxy's distance and chemical makeup. The signature was unmistakable: deep absorption breaks, red-shifted emission lines, and a spectral profile consistent with a structure from the cosmic dawn. JWST was not simply seeing the galaxy, it was hearing the universe speak through its light. Extracting that signal required stability. JWST orbits far from Earth at a point called L2, a gravitationally balanced location where the telescope can stay extremely still. Its sunshield blocks the heat of the Sun, Earth, and Moon, creating a stable environment where detectors can operate in silence. Without that stability, Canucks LRD Z8.6 would dissolve into background noise, indistinguishable from the infrared fog that fills space. In the end, the galaxy emerged not because it was bright, but because JWST was quiet. The telescope's silence allowed the universe to whisper, and in that whisper, scientists found a galaxy that had been waiting more than 13 billion years to be heard. The galaxy first appeared as a single reddish pixel. But hidden inside that pixel were detailed clues encoded in wavelengths. Astronomers extracted structure, composition, and motion from data that seemed too small to contain anything at all. At first glance, it did not look like a galaxy. It did not resemble anything familiar. Just one faint speck on an image, crowded with brighter, closer objects. Yet astronomers have learned that in the deepest reaches of the cosmos, a single pixel can hold an entire story. The early universe does not present itself boldly. It whispers through faint signals that must be interpreted carefully, layer by layer, until a picture emerges. To decode that single pixel, scientists turn to the language of spectroscopy. When stretched across billions of years, those fingerprints shift, but they do not disappear. JWST's instruments split the faint glow from the pixel into a spectrum, revealing subtle dips and rises. Each feature corresponded to specific atoms and molecules that absorbed or emitted light long before our solar system existed. These patterns told astronomers that the light came from a galaxy at extreme redshift. They revealed that the galaxy's stars were young and its gas was primordial. They even hinted at motion within the galaxy, showing that something inside was heating and disturbing the gas. The process is delicate. Extracting meaning from a single pixel requires removing noise, subtracting background glow, and adjusting for distortions created by gravitational lensing. The pixel must be cleaned and calibrated until only the true signal remains. Then, from that tiny fragment of light, scientists begin reconstructing the nature of the galaxy. Like hearing a distant echo and discerning the shape of the canyon that formed it, astronomers use these faint signatures to map a galaxy they cannot see directly. Even more remarkably, the velocity of gas within the galaxy can be measured from that tiny point of light. When gas moves toward us, its spectral lines shift slightly bluer. When it moves away, they stretch redder. The amount of shift tells us the speed. In Cannock's LRDZ 8.6, those shifts were larger than expected. Gas was racing around something massive, something powerful. It was the first hint that a supermassive black hole lived inside a galaxy, barely larger than a star cluster. Color gradients within the pixel also offered clues. If the red hue came only from cosmic expansion, the spectrum would show one pattern. But the galaxy displayed an additional redness caused by energetic processes inside it. This helped scientists distinguish between cosmic redshift and internal heat sources, further refining the picture hidden inside the pixel. In the end, a single point of light transformed into a detailed portrait of a galaxy from the universe's youth. It revealed stars forming under primitive conditions, gas swirling at high speeds, and the unmistakable presence of a giant hidden in its core. From one pixel, an entire world emerged. Cannock's LRDZ 8.6 formed when the universe was still in its assembly phase. Matter had only recently cooled enough to gather into clumps. Studying this galaxy reveals what galactic birth looked like before cosmic structure matured. In this era, the universe was still settling into the laws and patterns we now take for granted. Hydrogen and helium filled space like a vast, thin fog. Dark matter halos had begun to form, but they were small and scattered, their gravitational pull just strong enough to gather gas into primitive shapes. The universe had no grand spirals, no elliptical giants, no vast clusters. Everything was simple, raw, and newly formed. Galaxies like Cannock's LRDZ 8.6 were the first attempts of the cosmos to organize itself into something larger than isolated pockets of gas. These early galaxies were fragile. They lived in an environment shaped by rapid expansion and intense radiation left over from the Big Bang. Temperatures were dropping, but the universe had not yet become calm. The first stars had only recently ignited, creating bursts of ultraviolet light that pushed against the surrounding gas. Turbulence was common. Collisions between gas clouds sparked brief, chaotic bursts of star formation. The early universe was not a peaceful cradle. It was an unstable workshop where gravity worked over time to craft structure from near nothing. Cannock's LRDZ 8.6 emerged during this turbulent period. Its stars likely formed in short, intense episodes, driven by gas collapsing under gravity faster than it could disperse. These stars were unlike most in the modern universe. With no heavy elements to cool the gas efficiently, the early stars were larger, hotter, and more luminous. Their short lifespans meant that even by the time this galaxy released the light we see today, some of its earlier stars may have already exploded into supernovae, enriching the surrounding gas with the first traces of heavier elements. The galaxy's shape at this time would have been irregular and clumpy. Without well-defined disks or central bulges, early galaxies resembled loose collections of bright knots surrounded by diffuse gas. Gravity was still gathering material. Interactions with nearby protogalaxies distorted their structures. Collisions and mergers were common and played a major role in the early buildup of mass. Cannock's LRDZ 8.6 may have interacted with several smaller companions, each event adding new material and triggering new star formation. Yet, the most remarkable feature of this galaxy's birth environment was its scale. Everything was smaller. The dark matter halo anchoring it was tiny compared to modern galactic halos. The gas reservoir was limited. even the number of stars it could produce was modest. This makes the presence of a massive central black hole even more surprising. Somehow, in an era when galaxies struggled to form at all, this one grew a gravitational engine powerful enough to reshape its surroundings. Studying Cannax LRD Z 8.6 gives astronomers a rare glimpse into this unstable stage of cosmic evolution. It is a fossil from a time when galaxies were only beginning to appear, a clue to how the first structures assembled themselves in an unfinished universe. Through it, we are not just seeing a galaxy, we are seeing the universe learning how to build. Galaxies in this era were young, chaotic, and undersized. The universe had not existed long enough for them to accumulate large numbers of stars. This makes the presence of a powerful central engine even more surprising. In the epoch when Cannax LRD Z 8.6 existed, the universe was only a few 100 million years old. In cosmic terms, this is barely beyond infancy. Structures had only just begun to stabilize, and the process of building large galaxies was still far in the future. Even the Milky Way, which would eventually grow into a sprawling, star-filled spiral, began as a small, irregular patch of gas, much like this one. Growth takes time. Stars must form, live, and die. Gas must be recycled. Halos must merge. But at this early moment, none of that had happened yet. The universe simply had not given galaxies enough time to grow into anything substantial. Because of this limited time, early galaxies were dramatically smaller. Many contained only a few million stars compared to the hundreds of billions in galaxies today. Their dark matter halos were modest, their gas supplies thin, and their gravitational reach weak. They lived in crowded regions where every nearby structure tugged at them, pulling and stretching their shapes. Interactions were frequent and often violent, making it nearly impossible for galaxies to achieve any kind of stable form. They were more like growing embryos than fully realized structures. In such environments, star formation occurred in short, intense bursts. Gas would collapse under gravity, ignite new stars, and then be blown apart by stellar winds and explosions. This constant cycle prevented sustained growth. Stars formed quickly, but died quickly too. Their deaths enriched the surrounding gas, but the freshly enriched material often escaped into intergalactic space instead of staying within the galaxy. As a result, early galaxies did not retain enough material to build up mass efficiently. The most puzzling part of Cannax LRD Z 8.6 is not merely its small size. It is that within this small body, a supermassive black hole appears to have grown at an extraordinary rate. While the galaxy itself had limited resources, the black hole somehow acquired enough material to reach millions of solar masses. This imbalance challenges assumptions about how galaxies and black holes evolve together. In the modern universe, the black hole's size typically correlates with the galaxy's mass. Bigger galaxies host bigger black holes. But here, in this undersized early system, the black hole seems disproportionately large, as though it grew faster than the galaxy surrounding it. This mismatch suggests that growth in the early universe followed different rules. Galaxies were forming too quickly and too chaotically to maintain the delicate balance seen today. Matter could fall into a central black hole faster than it could assemble into stars. Gas clouds might collapse into dense cores that fed the black hole directly. In some cases, the black hole may have formed before the galaxy fully assembled, claiming a dominant role from the start. Cannax LRD Z 8.6 is a reminder that the early universe did not operate according to the stable patterns we observe now. There simply was not enough time for galaxies to grow as they do today. Yet somehow, in this rushed and chaotic environment, a cosmic giant emerged at the center of a tiny, unfinished galaxy. The galaxy's stars formed before the universe had built heavy elements. These metal-poor environments resulted in hotter, more massive stars that lived short, violent lives, influencing the galaxy's early development. In the earliest moments of cosmic history, the periodic table was almost empty. After the Big Bang, the universe contained only hydrogen, helium, and trace amounts of lithium. Everything else that makes stars complex, planets possible and chemistry interesting simply did not exist. There were no heavy elements to cool gas clouds, no dust grains to help collapse material, and no metals to regulate a star's temperature or longevity. When Canux LRD Z8.6 began forming its first stars, it did so in a universe that lacked the ingredients we now consider essential for stable, long-lived stellar populations. Under these primitive conditions, star formation behaved very differently. Without metals to radiate heat outward, collapsing gas clouds stayed hotter for longer. This meant they could not fragment as easily, which led to the formation of extremely massive stars. Some of them grew to dozens or even hundreds of times the mass of our Sun. These giants burned through their nuclear fuel at extraordinary speeds, shining with intense ultraviolet light that filled the young galaxy. Their brightness was unmatched, but their lives were brief. Many would have exploded as supernovae after only a few million years, leaving behind remnants that reshaped the surrounding environment. These massive stars played an essential role in the galaxy's early development. Their powerful radiation began ionizing hydrogen around them, carving out bubbles of hot plasma in a cold and mostly neutral universe. Their stellar winds pushed gas outward, clearing cavities and creating turbulent flows. Each explosion scattered new elements into space, enriching the galaxy with carbon, oxygen, and other building blocks that later generations of stars would incorporate. This cycle of birth and destruction created a dynamic environment inside Canux LRD Z8.6, one filled with both opportunities for new stars and barriers that prevented gas from settling into stable structures. In this era, galaxies formed stars in sharp bursts. Gas would collapse rapidly, form massive stars, and then be disrupted almost immediately by the energy those stars unleashed. The cycle repeated over and over, but without the efficiency of modern star formation. Only a small fraction of the galaxy's gas was converted into stars before being heated or pushed away. This helps explain why galaxies of this time remained small for so long. The early universe was full of energy and motion, and those forces made it difficult for stars to accumulate in large numbers. These early massive stars also illuminated the galaxy far more intensely than their modern equivalents. Their ultraviolet light contributed to the broader cosmic process of reionization, the era when the first luminous structures transformed the universe from opaque to transparent. Canux LRD Z8.6 would have been part of this transformation, with its giant stars punching holes of ionized gas through the surrounding fog. Studying these environments helps astronomers understand how the first stellar generations behaved and how their violent lives set the stage for everything that followed. In a universe without metals, stars were giants, their influence immediate and profound. They forged the first heavy elements, ignited the first bursts of intense radiation, and created the conditions that allowed galaxies to evolve beyond their earliest forms. Canux LRD Z8.6 carries the imprint of those stars, a fossil record of creation in a universe still learning how to build. Early cosmic gas behaved differently from gas in the modern universe. Without metals to cool it efficiently, some clouds collapsed directly, bypassing normal star formation. These conditions may explain the origin of giant black hole seeds. To understand why these early gas clouds behaved so strangely, we need to consider the simplicity of the universe at that time. The cosmic ingredients list was short. Hydrogen was abundant, helium was present in smaller amounts, but that was it. Without heavier elements to radiate away heat, gas could not cool and settle into small, dense pockets. Instead, it remained hot, smooth, and resistant to fragmentation. This lack of fragmentation meant that in some regions, entire clouds of gas collapsed inward as massive units, rather than breaking apart into many smaller stars. These collapsing giants had no modern equivalent. They were immense structures shaped purely by gravity and primordial physics. When such clouds contracted, they reached extreme densities and temperatures. At these thresholds, something remarkable could happen. Instead of forming a cluster of stars, the entire cloud might collapse directly into a single object with a mass tens or hundreds of thousands of times that of the Sun. These objects are known as direct collapse black hole seeds. They are not the remnants of dead stars. They are born large. They form with enough mass to begin shaping their surroundings immediately, long before galaxies become mature. In a galaxy like Canucks LRDZ 8.6, these conditions could easily have occurred. The environment was chaotic, with frequent mergers between gas-rich halos. Each merger funneled enormous amounts of material toward the center, creating streams of gas that piled up faster than radiation could push them apart. If one of these inflows gathered enough mass, it could trigger a runaway collapse. In that collapse, there would be no supernova, no bright stellar core, only an instant plunge toward a single gravitational center. This process may explain why some early black holes grew so rapidly. While typical black holes begin as the cores of dead stars, direct collapse seeds skip that phase entirely. They start with a head start, already possessing millions of times more mass than a stellar remnant. In the rapidly evolving environment of the early cosmos, even small advantages became enormous over time. A black hole born with a massive seed could pull in gas more effectively, dominate the galaxy more quickly, and reach supermassive status while the rest of the galaxy was still forming its first generations of stars. The existence of Canucks LRDZ 8.6 supports this idea. The galaxy is too young and too small for a black hole to have grown to its observed size through normal processes alone. Something must have accelerated its growth. A direct collapse seed offers a compelling explanation. It could form one almost immediately, altering the trajectory of its entire evolution. These early gas clouds represent one of the universe's most intriguing pathways for creation. They show that sometimes gravity does not build stars. Sometimes it skips straight to building giants. Matter was not yet plentiful. Feeding a black hole in this era required capturing sparse gas drifting in expanding space. Yet evidence suggests this black hole consumed material at a furious rate, despite the scarcity. In the early universe, black holes were born into a landscape that was far less cooperative than the one we see today. Gas was thinly spread across vast distances, pulled apart by cosmic expansion, and constantly stirred by young stars releasing intense radiation. In such an environment, you would expect black holes to starve. The ingredients required for rapid growth simply were not abundant. Yet somehow, the black hole inside Canucks LRDZ 8.6 managed to grow at a rate that defies expectations. It fed as though it lived in a universe rich with material, even though the cosmos had barely begun to organize itself into the structures that normally supply black holes with their fuel. To understand how this was possible, we must consider the nature of gas flow in the young universe. Gas was not uniform. It flowed along filaments of dark matter that acted like invisible scaffolding, guiding matter toward denser regions. Even in a low-density cosmos, these filaments could concentrate streams of gas into narrow pathways. If a forming galaxy happened to sit at one of these intersections, it could receive a steady influx of material delivered by gravity itself. Canucks LRD Z8.6 may have occupied one such location, giving its central black hole access to a pipeline of gas in an era where most regions had almost none. Black holes do not simply swallow matter whole. They influence their surroundings through gravity, pulling gas inward in spiraling flows. As gas falls toward a black hole, it heats up, creating a bright disk of glowing material. The faster a black hole accretes gas, the brighter and hotter this disk becomes. In the case of Canucks LRD Z8.6, the spectral signatures suggest that gas was falling inward at speeds far faster than expected for a galaxy this small. Instead of a slow, gentle trickle, the black hole was consuming material at a rate that may have exceeded the Eddington limit, a theoretical boundary that describes how quickly a black hole can grow without blowing away its own fuel. In the early universe, however, conditions may have allowed black holes to bypass this limit. Dense pockets of gas, gravitational inflows, and chaotic motion could have compressed material enough to overwhelm the outward pressure from radiation. If that happened here, the black hole could have grown rapidly despite the universe's overall scarcity. gas would have been torn apart by tidal forces, heated to millions of degrees, and swept into the black hole in bright, energetic pulses. This rapid feeding would have shaped the galaxy around it. As the black hole consumed material, it also released radiation and outflows that disturbed surrounding gas. These disturbances could have halted star formation in some regions, redirected gas into new pathways, or triggered further collapse. In this way, the black hole was not just a consumer, it was an active participant in the galaxy's growth, a gravitational engine operating at full strength in a time when very little else had reached such maturity. What makes this black hole remarkable is not just its size, but the conditions under which it grew. In a cosmos that was still forming its first structures, it managed to thrive. Somehow, in a universe too young and too empty for such behavior, a giant found a way to feed. Spectral lines from the galaxy reveal gas moving at extraordinary speeds. Extracting those motions required precision measurements, where even a small error could erase the entire signal. This segment examines how astronomers measure motion in the early universe. When astronomers look at a galaxy as distant as Canucks LRDZ 8.6, they are not observing a familiar picture with clear details. They are studying light that has been stretched, dimmed, distorted, and weakened by more than 13 billion years of travel. The signal arrives faint and fragile, buried beneath natural background glow. Detecting motion inside such a distant object is like listening for the vibration of a single violin string during a thunderstorm. Yet, with the tools aboard the James Webb Space Telescope, scientists can do exactly that. The key lies in the subtle patterns etched into the galaxy's spectrum. Every atom and molecule absorbs and emits light at specific wavelengths. These appear as thin lines across the spectrum, like marks on a ruler. If the gas inside the galaxy is moving, those lines shift slightly. Motion toward us makes them shorter and bluer. Motion away stretches them to redder wavelengths. The amount of shift reveals the speed. The trick is measuring this shift with enough accuracy to distinguish movement from noise. For a galaxy as faint as this one, the lines are incredibly weak. They blur easily. The slightest instrumental vibration or calibration error can distort them. JWST's stability is what makes the measurement possible. Floating far from Earth, shielded from heat and vibration, the telescope provides a steady platform where even the smallest spectral shift can be captured without interference. But the challenge doesn't end there. Before astronomers can measure the motion inside the galaxy, they must remove the effects of cosmic redshift, which stretches the entire spectrum like a rubber band. Only after accounting for this global shift can the tiny internal variations be isolated. Once the spectrum is cleaned, astronomers search for subtle asymmetries. Some regions of gas emit slightly bluer light, others emit light that is slightly redder. These patterns reveal how gas rotates or flows through the galaxy. In Canucks LRDZ 8.6, the shifts were larger than expected. Gas was not drifting slowly through a calm environment. It was racing around at high speeds, stirred by intense gravitational forces. These velocities pointed unmistakably to a massive central object. What makes this measurement remarkable is not only the faintness of the signal, but the fact that the galaxy is too small to resolve directly. Astronomers cannot see separate regions spinning. They rely entirely on variations in the spectrum to decode what is happening inside. It is a reconstruction based on indirect evidence, the scientific equivalent of deducing the layout of a distant city by listening to the echoes of its traffic. Through this method, astronomers uncovered the hidden dynamism of a galaxy that appears as a single pixel. They revealed streams of gas whipping around at hundreds of kilometers per second, influenced by a gravitational force that should not exist in a galaxy this young. These measurements show that even at the edge of detectability, the universe leaves clues. If the tools are quiet enough and the analysis precise enough, motion can be heard across billions of years. Canucks LRDZ 8.6 is not just small, it is so compact that some star clusters in the Milky Way are physically larger. Understanding how something so tiny sustained a central monster is a puzzle scientists are still working to solve. When astronomers first estimated its size, they were struck by how minuscule the galaxy truly is. In the modern universe, galaxies stretch across tens or hundreds of thousands of light years. Even the dwarf galaxies orbiting the Milky Way extend for thousands of light years. But Cannock's LRD Z8.6 measures only a fraction of that scale. Its entire stellar population fits into a region smaller than some of our Milky Way's dense globular clusters, those ancient spherical swarms of stars that hang quietly in our galactic halo. To find a supermassive black hole lodged inside an object of comparable size is something unprecedented. Mapping such a compact galaxy is a delicate task because it cannot be resolved into individual stars. Instead, astronomers must infer its structure from the shape and brightness pattern of the smeared image created by gravitational lensing. Every pixel in the observation contains blended light from thousands of stars stretched across cosmic time. Understanding the layout of this galaxy requires reconstructing an image distorted by a cosmic magnifying glass. Researchers use sophisticated lensing models, bending and unbending the path of light mathematically until the true form of the galaxy emerges. These models reveal more than just size. They show how starlight is distributed, how concentrated the core is, and whether the galaxy contains clumps or smooth regions. In the case of Cannock's LRD Z8.6, the light profile indicates a central brightness spike much sharper than expected for such a small system. This spike suggests not only a dense core but the influence of something gravitationally dominant at the center. Even from its faint signal, the galaxy betrays the presence of its hidden giant. The compactness of Cannock's LRD Z8.6 also raises questions about how such a small system could supply enough gas to feed a rapidly growing black hole. In larger galaxies, gas flows inward from spiral arms, mergers, and extended halos. But here, the supply had to come from a tiny reservoir. One possibility is that the galaxy resides inside an unusually dense pocket of cosmic gas, allowing material to funnel inward more efficiently than its size suggests. Another is that early dark matter halos were more concentrated, creating deeper gravitational wells that trapped gas effectively. Compact galaxies are not unknown in the early universe, but few have shown signs of hosting active black holes. Most small early galaxies appear as faint, irregular patches of star formation. What makes this one remarkable is the combination of its size and the unmistakable evidence of a central engine. The black hole did not simply coexist with its galaxy, it dominated it. Even in its earliest years, the galaxy seems to have orbited around the black hole's needs rather than the other way around. Mapping Cannock's LRD Z8.6 therefore becomes more than an exercise in measuring distance or size. It becomes a key to understanding how the earliest structures in the cosmos were built. With so few stars, so little mass, and such small physical scale, this galaxy should not have been capable of hosting a giant. And the map of its compact shape is the first clue to unraveling how that improbable pairing came to be. Even in a galaxy this small, the black hole likely exerted major influence. It may have heated gas, stopped star formation, or even blown material out of the system entirely. Here we explore the physical feedback without repeating earlier segments. In the astrophysical world, black holes are not merely passengers inside galaxies, they are engines. In large galaxies, this influence can regulate the formation of stars and maintain balance within vast clouds of gas. But in a tiny galaxy like Cannock's LRD Z8.6, the black hole's power would have been disproportionate. It would have been like placing a furnace inside a small room. Even a modest outflow of energy could have reorganized the entire system. The process begins with accretion. As gas spirals toward the black hole, friction and compression heat it to extraordinary temperatures. This material forms an accretion disk that shines with intense ultraviolet and X-ray radiation. In a galaxy as compact as this one, that radiation would not fade into the background. It would sweep across the entire system, altering temperature, pressure, and the chemistry of the surrounding gas. This illumination could have ionized large regions of the galaxy, creating pockets where star formation became difficult or even impossible. Alongside radiation, feeding black holes launch winds. These are not gentle breezes but powerful flows of particles accelerated by magnetic forces near the event horizon. In massive galaxies, such winds carve channels through dense gas. In Canucks LRDZ 8.6, they may have done far more. The galaxy's shallow gravity well would have struggled to retain its gas when hit by these outflows. Some of the material intended for future star formation could have been expelled outright, lost to intergalactic space. This would slow the galaxy's growth and leave behind a star field far smaller than what the black hole's age might suggest. There is also the possibility of jets. Some black holes eject narrow streams of high-energy particles that travel at nearly the speed of light. If such jets existed here, they would have pierced through the galaxy in fractions of a second, heating and compressing gas clouds. Depending on direction and strength, jets can either trigger new star formation or quench it entirely. In a galaxy this small, even a short-lived jet could have influenced the entire structure. These feedback effects create a cycle. The black hole consumes gas, produces energy, and expels part of the material needed for future growth. This process shapes the galaxy's ability to evolve. In larger systems, the cycle is balanced over time. In early miniature galaxies like Canucks LRDZ 8.6, the effect would have been amplified. The black hole may have set the limits on how large the galaxy could become, dictating the number of stars produced and the availability of cold gas. Understanding the black hole's influence provides insight into why the galaxy remained so small. The black hole may have dominated its environment from an extremely early stage, asserting gravitational and energetic control before the galaxy had a chance to accumulate mass. In this sense, the black hole was not just housed by the galaxy, it was one of the architects of its final form. In Canucks LRDZ 8.6, the giant at the center shaped the tiny world around it, leaving behind a fossil of early cosmic feedback during the universe's formative years. Ionized gas is a diagnostic tool. By analyzing how atoms lose electrons in intense radiation, astronomers reconstruct the conditions surrounding early galaxies. This reveals temperature, density, and the presence of extreme UV light. The presence of ionized gas inside a galaxy as small and ancient as Canucks LRDZ 8.6 is more than just an interesting observation, it is a message. Ionization occurs when atoms are exposed to radiation so energetic that it strips electrons away. This process does not happen in calm or quiet environments. It requires powerful sources of ultraviolet or X-ray light. In the early universe, these sources typically came from either very massive young stars or feeding black holes. By examining the patterns left behind in the ionized gas, astronomers can determine which of these forces dominated the galaxy's interior. The key lies in the spectral lines. When an atom loses an electron, it leaves behind a distinct signature in the light it emits. Different levels of ionization produce different fingerprints. For example, if oxygen is ionized once, it emits one pattern. Ionized twice, it emits another. In Canucks LRDZ 8.6, the signatures show high-energy ionization states that early stars alone struggle to produce. These patterns point toward a concentrated source of extreme radiation, consistent with an actively feeding black hole buried in the galaxy's core. But ionization tells us more than the presence of radiation. It reveals temperature and density as well. Hot gas emits broader, more energetic lines, while cooler gas emits narrow ones. Dense gas absorbs and scatters radiation differently from thin gas. By combining these clues, astronomers reconstruct a portrait of the galaxy's internal environment. They can estimate how much gas was available for star formation, how turbulent the region was, and how far the black hole's influence extended. In Canucks LRDZ 8.6, the gas appears to be both hot and highly disturbed. This suggests that radiation from the central engine permeated much of the galaxy, heating the surrounding medium and altering its structure. In more mature galaxies, these ionization zones often appear near the core, but in a galaxy this small, the entire system can be affected. A single burst of ionizing radiation may sweep through the galaxy in a relatively short time, reshaping the environment for millions of years afterward. Ionized gas also helps determine how quickly the galaxy was forming stars. When gas becomes too hot, it loses the ability to collapse into new stars. If ionization was widespread, star formation may have been interrupted or slowed significantly. The intermittent nature of early star formation matches this scenario. Bursts of intense radiation from massive stars or black hole activity would ionize gas, pause star formation, and then fade, allowing gas to cool and collapse again. This ebb and flow creates a dynamic environment where the galaxy evolves in fits and starts, driven largely by the balance between cooling gas and bursts of ionizing radiation. For astronomers, the state of the gas inside Canux LRD Z8.6 provides a rare snapshot of these cycles in action. Through ionized gas, we glimpse the interplay of forces inside one of the earliest galaxies ever observed. It reveals a place shaped by radiation, turbulence, and energy far greater than its tiny size suggests. And it confirms that even in the earliest times, galaxies were complex ecosystems molded by both starlight and something far more powerful. Its deep red color carries meaning. Redshift stretches light across expanding space, but dust and gas also contribute. By analyzing its color profile, scientists determine how much of the redness is cosmological and how much comes from internal processes. In the distant universe, red is more than a color. It is a clock. The farther a galaxy lies, the more its light is stretched by the expanding fabric of space. This stretching shifts shorter wavelengths into longer ones, turning blues into reds and visible light into infrared. By the time the light from Canux LRD Z8.6 reaches us, it has traveled for more than 13 billion years. During that journey, the universe expanded dramatically, stretching the wavelength so far that the galaxy appears as a faint red dot in JWST's infrared sensors. But astronomers quickly noticed something unusual. The galaxy was redder than its extreme distance alone could explain. To understand this deeper redness, scientists examined the galaxy's color profile, a measurement of brightness across different wavelengths. If redshift were the only factor, the spectrum would follow a smooth, predictable pattern. Instead, the profile shows additional dimming at shorter wavelengths, suggesting that something inside the galaxy is absorbing or scattering light. In galaxies like this one, two major culprits can cause this effect: dust and energized gas. Dust at this early time is a rare commodity. Heavy elements that form dust grains are created only in the deaths of stars, yet stars had not existed for very long. The presence of any dust at all implies that massive stars formed quickly and exploded soon after, enriching the galaxy earlier than expected. Even a small amount of dust can redden the galaxy's light by blocking shorter wavelengths more effectively than longer ones. This early dust hints at a rapid cycle of star birth and destruction, which aligns with other clues about the galaxy's turbulent youth. The second contributor is energetic gas, heated by intense ultraviolet and X-ray radiation. This gas scatters and absorbs light unevenly, altering the galaxy's color signature. In Canux LRD Z8.6, the spectral patterns reveal ionized regions that glow brightly at certain wavelengths, while dimming others. This energetic environment likely stems from the galaxy's central black hole. As it accretes gas, it floods the surrounding space with high-energy photons, creating bubbles of ionized gas. These bubbles trap and re-emit light in ways that skew the galaxy's overall color. By separating the effects of dust, gas, and redshift, astronomers construct a more complete picture of the galaxy's interior. The deeper red tone indicates that the galaxy is not simply distant but actively shaped by internal forces. It suggests bursts of star formation that produced enough dust to alter the spectrum, alongside a powerful central radiation source that further shifts the color profile. Even in its infancy, Canux LRD Z8.6 shows signs of complexity usually found in much older systems. This unexpected redness also helps refine estimates of the galaxy's age and composition. It hints at the presence of early metals and energetic processes, suggesting that the galaxy evolved rapidly despite its small size. The color becomes a clue, pointing to internal activity far greater than the galaxy's faint appearance initially implies. By studying why this tiny galaxy glows so red, astronomers uncover the physical conditions that shaped its early life. In this case, the color reveals a world influenced by dust, radiation, and a powerful hidden engine, far from the simple object its faint glow suggested. Light from Cannock's LRD Z8.6 helps refine measurements of how quickly the universe expanded during its earliest phases. Each ancient galaxy serves as a calibration point for cosmological models. When we look at a distant galaxy, we are not just observing a faraway world. We are observing the rate at which space itself has stretched. The light from Cannock's LRD Z8.6 left its home when the universe was still young, traveling through expanding space that steadily pulled each wavelength apart. This stretching, known as redshift, holds the key to unlocking the universe's expansion history. By pinpointing exactly how far the galaxy's light has shifted, astronomers gain a clearer picture of how fast the cosmos was growing at the time that light was emitted. Redshift does not simply tell us distance, it tells us time. Cannock's LRD Z8.6 sits at a redshift of approximately 8.6, meaning we observe it as it existed just a few 100 million years after the Big Bang. This makes it a valuable data point in a region of cosmic history where observations are still sparse. Each new galaxy discovered from this time acts like another tick mark on a ruler used to measure the universe's expansion. To refine cosmological models, astronomers feed redshift data into mathematical frameworks that describe how space evolves. These models predict how much matter and energy existed at different stages, how gravity slowed expansion, and how dark energy later accelerated it again. The early universe sits at a delicate intersection where gravity dominated more strongly than it does today, shaping the growth of the first structures. Observing galaxies like Cannock's LRD Z8.6 helps test whether our models match the actual pace of expansion during those early times. The light from this galaxy also interacts with the material it passes through. Along its journey across billions of years, it traveled through regions filled with neutral hydrogen, ionized gas, and evolving cosmic structures. These interactions leave subtle imprints on the spectrum, offering clues about the density of matter the light encountered. By analyzing these imprints, astronomers can estimate how much hydrogen filled the early universe and how quickly it transitioned from opaque to transparent during the era known as cosmic reionization. This transition is tied directly to the expansion rate, making each measurement a piece of a larger puzzle. Because Cannock's LRD Z8.6 lies behind a gravitational lens, its light is magnified and distorted in a predictable way. The lensing effect itself depends on the geometry of the universe, including its expansion. By modeling the lens and comparing predicted distortions with actual ones, scientists can further constrain cosmological parameters. This adds another layer of information, sharpening our understanding of how space stretched between the time the light was emitted and the time it reached JWST. Together, these factors make ancient galaxies like Cannock's LRD Z8.6 essential tools for cosmic measurement. They help refine the timeline of expansion, test the consistency of cosmological equations, and reveal how quickly the universe transitioned from primordial simplicity into the complex cosmic web we observe today. By studying a single galaxy's journey through expanding space, astronomers piece together the story of how the universe grew, stabilized, and eventually produced galaxies like our own. The gas within this galaxy is not calm. It moves in chaotic, turbulent flows. This turbulence is a sign of the universe's violent early conditions and provides clues about how structure formed under cosmic pressure. The first billion years of the universe were anything but peaceful. Matter was still settling into the gravitational wells carved by dark matter. Gas clouds collided, merged, tore apart, and reassembled under the relentless tug of gravity. In this environment, turbulence was the rule rather than the exception. For a small galaxy like Cannock's LRD Z8.6, the turbulence was not just a background phenomenon. It shaped the galaxy's structure. its ability to form stars. When astronomers study the spectral lines from this distant galaxy, they notice that the lines are not narrow and orderly. Instead, they are broadened and distorted, signs that gas is moving at many different speeds and in many different directions. These irregularities are fingerprints of turbulence. Gas is not rotating smoothly around the galaxy. It is swirling in knots, streaming in chaotic patterns, compressed in some regions and stretched in others. This behavior is consistent with galaxies still learning how to gather themselves into stable structures. Turbulence of this kind arises from a variety of early universe forces. One of the most important is the inflow of cold gas along dark matter filaments. These filaments serve as cosmic highways, channeling material toward developing galaxies. But the gas does not arrive gently. It crashes into existing clouds, sending shockwaves through the system. These shocks stir the gas into motion, increasing temperature and pressure. If dense enough, they can also trigger rapid star formation, leading to bursts of young stars that further disturb the environment. Another source of turbulence is feedback from those very stars. In a metal-poor galaxy like Canucks LRD-Z 8.6, the first generations of stars were enormous and short-lived. Their ultraviolet radiation and powerful stellar winds injected energy into the surrounding gas, stirring it like a storm. When these massive stars exploded as supernovae, they blasted material outward, adding new waves of turbulence and reshaping the galaxy's internal flows. Each explosion compressed some regions while hollowing out others, creating a patchwork of pressures and densities that would take millions of years to settle. The presence of an active black hole in the center would have amplified these effects. As the black hole fed, it emitted intense radiation and may have launched winds of its own. These outflows pushed against the gas, adding more chaotic motion to the already unstable environment. In a galaxy this small, even a brief episode of black hole activity could churn the entire system, introducing turbulence far out into its outer regions. Turbulence is not just a sign of violence, it is also a key ingredient in galaxy formation. Chaotic motion mixes gas, distributes energy, and helps regulate when and where new stars can form. Without turbulence, the galaxy might collapse too quickly or form too many stars too early. With too much turbulence, star formation would stall entirely. The balance inside Canucks LRD Z 8.6 offers clues about how the earliest galaxies found a middle ground. By studying turbulence in this ancient system, astronomers learn not just about one galaxy, but about the conditions that shaped the universe's first billion years. Turbulence reveals a cosmos still unsettled, still forming, and still full of the raw energy that would eventually sculpt the galaxies we see today. Spectral analysis reveals which elements existed in the galaxy at that time. This chemical fingerprint shows how far star formation had progressed and whether earlier stars had already enriched the environment. When astronomers examine a galaxy from the early universe, they are not simply looking at light, they are reading a chemical record. Every star that has ever formed, lived, and died leaves behind a trace in the surrounding gas. Those traces appear as tiny features in the spectrum. Dips where specific wavelengths are absorbed, peaks where certain elements glow. These features act like a signature, allowing scientists to determine which elements were present and in what quantities. Even across billions of years, these chemical fingerprints remain readable. In the earliest epochs, most galaxies contained only hydrogen and helium, the two simplest elements forged during the Big Bang. Everything else had to be created through stellar processes. When massive stars exploded, they produced oxygen, carbon, nitrogen, and heavier elements, scattering them into space. The presence of these elements inside Canucks LRD Z 8.6 tells us that at least one generation of massive stars must have already lived and died by the time the galaxy emitted the light we now see. This means the galaxy was not a pristine system. It had already undergone cycles of creation and destruction despite its tiny size and youth. The specific elements detected in the spectrum reveal even more. Oxygen, for example, forms in the cores of massive stars and is released during supernova explosions. Its presence suggests that energetic events shaped the galaxy early on. Carbon and nitrogen point to intermediate mass stars contributing material over slightly longer timescales. Each element traces a different stellar process, allowing scientists to piece together the sequence of events that enriched the galaxy. Even the absence of certain elements can be telling. A lack of heavier metals like iron would indicate that only the earliest types of supernovae had occurred, perhaps not enough time having passed for slower enrichment processes. Chemical fingerprints also reveal temperature and physical conditions. The strength of certain emission lines depends on how hot the surrounding gas is and how many electrons atoms are losing or gaining. In Canucks LRD Z 8.6, the patterns suggest a hot, energetic environment, likely influenced by intense star formation and possibly by the central black hole. Ionized oxygen lines, in particular, point toward powerful ultraviolet radiation permeating the galaxy, consistent with both massive stars and an active nucleus. The distribution of elements also tells us how efficiently the galaxy formed stars. If enrichment is patchy, with some regions showing more metals than others, it suggests localized bursts of star formation. If the enrichment is uniform, it implies that turbulent mixing distributed elements quickly throughout the system. Early galaxies often show uneven enrichment because their small size and chaotic conditions limit how thoroughly materials can mix. In this case, the chemical fingerprint hints at a complex and dynamic environment where different pockets of gas experience different histories. Finally, studying these elements helps determine whether the galaxy had time to recycle its material. In larger galaxies, supernovae enrich gas that later forms new stars. But in a small galaxy like Canucks LRDZ 8.6, strong outflows may have expelled much of that enriched gas into intergalactic space, slowing future star formation. If certain elements appear in low abundance, it may mean the galaxy could not hold on to the products of its first stars. By examining the chemical fingerprint of Canucks LRDZ 8.6, astronomers uncover a detailed record of its earliest generations. It is a glimpse into a period when stars were still forging the universe's first heavy elements, shaping the chemistry that would one day make planets, life, and everything familiar possible. Despite being too small to image directly, astronomers reconstruct its structure using indirect methods. Light distribution, velocity fields, and modeling allow scientists to infer the galaxy's size, shape, and density. Most galaxies in the nearby universe can be imaged in beautiful detail. Spiral arms, glowing nebulae, and star clusters appear clearly through modern telescopes. But galaxies from the universe's earliest eras are far beyond the reach of direct imaging. They are too small, too distant, and too dim for even the most advanced instruments. Canucks LRDZ 8.6 falls deep into this category. Its entire structure collapses into a single blurred point of light on JWST's detectors. Yet despite this limitation, astronomers can still reconstruct it. They can infer its size, its concentration of stars, and even its density, using techniques designed to extract meaning from the faintest of signals. Reconstruction begins by analyzing how its light is spread across the lens-distorted image. Gravitational lensing stretches, magnifies, and warps the incoming signal. By modeling the mass distribution of the foreground galaxy cluster, astronomers can reverse that distortion, mapping the smeared arc of light back to its original shape. This process is like watching an image reflected in rippling water and mathematically smoothing out the waves. It does not reveal crisp details, but it provides a reliable outline of the galaxy's true form. Once the distortion is undone, astronomers examine the brightness profile. Even a galaxy that appears as a single pixel contains subtle gradients. The center may glow slightly brighter, while the edges fade into background noise. These gradients follow physical patterns that reflect underlying structure. In Canucks LRDZ 8.6, the light falls off steeply toward the edges, indicating a compact system with a dense core. This rapid decline in brightness suggests that most of the stars are packed tightly together, far more tightly than in most modern galaxies. Velocity fields offer another clue. By analyzing tiny shifts in the galaxy's spectral lines, scientists measure how gas moves inside the system. The pattern of these shifts reveals whether the galaxy rotates, collapses, or swirls in chaotic flows. Even if the galaxy cannot be resolved into separate regions, the combined motion leaves a statistical signature. For Canux LRDZ 8.6, the velocities are high and disordered, hinting at a turbulent, crowded environment shaped by strong gravitational forces. Modeling ties everything together. Astronomers create simulations of galaxies with different sizes, shapes, and densities. They compute how each model would appear through a gravitational lens and at extreme distances. Then they compare those simulated appearances to the actual image, narrowing down the possibilities. This iterative process eventually converges on a structure that best matches the observed light. It shows that Canux LRDZ 8.6 is incredibly small, compact, and dense, with a structure more akin to an oversized star cluster than a mature galaxy. This reconstruction teaches us that seeing is not always necessary to understand. In astronomy, information does not always arrive in clear pictures. Sometimes it comes in fragments, distortions, and faint impressions that must be pieced together. Through careful modeling, subtle measurement, and an understanding of how light behaves across cosmic distances, scientists can reveal the hidden architecture of a galaxy we cannot see directly. In the case of Canux LRDZ 8.6, these techniques uncover a tiny world shaped by intense forces holding together around a gravitational giant at its core. Even blurred by time and distance, the galaxy reveals its secrets to those who know how to read its light. Every galaxy is anchored by a halo of dark matter. The properties of Canux LRDZ 8.6 give insight into how small halos formed and how they gathered baryonic matter in the early universe. In the modern universe, galaxies sit comfortably inside vast cocoons of dark matter. These halos stretch far beyond the visible stars, acting as gravitational scaffolding that holds galaxies together. But in the early universe, halos were small, loosely bound, and only beginning to emerge from the cosmic web. Canux LRDZ 8.6 represents one of these first gravitational seeds, a tiny condensation of dark matter that managed to collect enough ordinary gas to form a galaxy. Studying such an early system gives astronomers a rare glimpse into how the cosmic landscape was shaped before galaxies became large, stable, and familiar. Dark matter halos form when invisible matter collapses under its own gravity, creating dense knots where gas can gather. In the early universe, these halos were not yet massive. They were the size of small towns in comparison to the sprawling cities they would one day become. Yet even these miniature halos had an important job. They provided gravitational wells deep enough to trap the first gas that drifted through space. Without them, gas would have remained too diffuse to ignite star formation. Canux LRDZ 8.6 sits inside one of these early wells, and the galaxy's compactness hints that the halo must have been tightly concentrated. The strength of the halo can be inferred from how the galaxy's gas moves. The high velocities measured within Canux LRDZ 8.6 suggest that gravity is strong despite the galaxy's small size. Since the stars and gas alone cannot account for this strength, the remainder must come from dark matter. This implies that the halo is not only present, but unusually dense. Such halos were predicted in simulations of the early universe, but have rarely been observed so clearly. Their existence supports the idea that early galaxies formed in pockets of dark matter where density peaks were sharper and more compact than those of later epochs. Another important clue lies in how the halo gathered baryonic matter. In many early systems, the inflow of gas was chaotic and uneven. Gas traveled along thin filaments of the cosmic web, falling into halos in streams rather than smooth flows. If Canux LRDZ 8.6 is indeed anchored by a dense halo, it may have captured gas more efficiently, allowing the tiny galaxy to form stars earlier and more vigorously. This rapid infall could also have fed the central black hole, giving it the fuel it needed to grow to such an unexpected size. But these halos also faced challenges. Their small masses made them vulnerable to feedback from stars and black holes. A strong burst of radiation or a cluster of supernovae could push gas out of the halo entirely, preventing further star formation. The fact that Cannock's LRD Z8.6 retained enough gas to build a galaxy suggests that its halo was just strong enough to hold everything together, resisting the violent forces within. In this sense, the galaxy tells a story not just about itself, but about the invisible foundation beneath it. Cannock's LRD Z8.6 is a window into the earliest stages of dark matter halo formation, showing how the first cosmic structures emerged from darkness to shape the universe we see today. Young galaxies often produce strong winds driven by massive stars and black hole activity. These winds sculpted early structure, redistributed matter, and influenced future star formation. In the early universe, winds were not gentle breezes drifting through calm star fields. They were powerful, high-velocity flows of gas and radiation that surged outward from the brightest and most violent objects. Massive stars, only a few million years old, generated winds through intense ultraviolet radiation and rapid stellar rotation. Their outer layers were blown away at thousands of kilometers per second. In small galaxies like Cannock's LRD Z8.6, these winds could cross the entire system in a relatively short time, carrying energy and matter into every corner of the young galaxy. When these massive stars reached the end of their brief lives, their supernova explosions amplified the effect. A single supernova can release more energy in seconds than our Sun will produce in its entire lifetime. In larger galaxies, this energy disperses across vast distances. But in a compact early galaxy, the shockwaves ripple outward with tremendous force. They compress gas in some regions, triggering star formation, while clearing gas from others, suppressing it. In this way, winds do not simply move matter, they write the rules for when and where stars can form. Black hole activity adds another layer of complexity. As the central black hole in Cannock's LRD Z8.6 consumed gas, it released radiation and sometimes expelled material in powerful outflows. These outflows could take the form of broad winds driven by intense heat near the accretion disk, or even narrow jets accelerated by magnetic fields. If either of these phenomena occurred, they would have reshaped the internal environment dramatically. In a galaxy this small, the entire system could be influenced by a single episode of black hole activity. These winds and outflows also redistributed matter. Gas rich in heavy elements, produced by the first generations of stars, might be pushed outward into the galaxy's outer regions, or even expelled into intergalactic space. This movement of metals plays a critical role in early galaxy evolution. Regions that receive enriched gas can form more complex stars and begin to develop dust. Regions cleared by winds remain primitive, forming stars with fewer heavy elements. The chemical diversity of Cannock's LRD Z8.6 may reflect this constant tug-of-war between enrichment and removal. Winds also shape the galaxy's structure. In a small, fragile system, repeated pushes and shocks can prevent a stable disk from forming. Gas that might have settled into a rotating structure instead becomes turbulent and uneven. This turbulence influences the gravitational potential, star formation rates, and even the efficiency with which the galaxy collects new material from the cosmic web. Over time, outflows could determine whether the galaxy grows steadily, stagnates, or even loses its ability to form stars at all. The presence of strong winds in the early universe helps explain why tiny galaxies like Cannock's LRD Z8.6 remained small, even though they received inflows of gas from dark matter filaments. Much of that gas was pushed back out by stellar and black hole feedback. Growth became a delicate balance between gaining material from the universe and losing it through violent winds. In this ancient galaxy, winds were not merely consequences of star formation. They were active participants in shaping the system's evolution. They carried the energy of young stars, the force of supernovae, and the influence of a hidden giant, sculpting a galaxy that, despite its small size, experienced some of the most dramatic forces in the cosmos. The existence of such a massive black hole in such a small galaxy forces astrophysicists to revise or extend parts of galaxy formation theory. This segment focuses on model adjustment, not repetition of the anomaly itself. In modern cosmology, galaxies and black holes are thought to grow together. As galaxies accumulate gas and stars, their central black holes feed and expand in sync. This relationship is so well behaved in the nearby universe that astronomers have derived precise scaling laws linking a galaxy's mass to the size of the black hole at its core. Yet Cannock's LRDZ 8.6 challenges this harmony. The galaxy is tiny, but the black hole at its center appears far too large for its surroundings. This mismatch does not simply break an observational pattern. It forces theorists to reconsider how galaxies and black holes formed in the earliest epochs. One of the first revisions involves the timeline of growth. Traditional models assume black holes start small, born from the remnants of the first stars, and grow steadily as galaxies evolve. But to reach the mass suggested in Cannock's LRDZ 8.6, the black hole must have grown far more rapidly than models allow. This means either the seed started larger than expected, or the early universe provided growth mechanisms not fully captured in current simulations. Researchers must now expand their models to include accelerated feeding scenarios, direct collapse pathways, or early environments with densities higher than previously assumed. Another adjustment concerns feedback regulation. In later galaxies, feedback from black holes, radiation, winds, and jets limits growth by heating or expelling gas. This keeps black holes and galaxies evolving in lockstep. But in the early universe, feedback may have behaved differently. If radiation escaped more easily, or if gas inflow was more concentrated, black holes might have been able to grow without immediately disrupting their hosts. The discovery of Cannock's LRDZ 8.6 suggests that early galaxies lacked the stability and scale needed for self-regulating feedback, allowing black holes to expand unchecked. This forces theorists to revise how feedback processes operate at extreme redshift. Cosmologists also need to reconsider the distribution of dark matter in early halos. A disproportionately large black hole implies a deep gravitational well at the galaxy's center. If dark matter halos were denser or more concentrated during the universe's early stages, they could have funneled gas toward the core more effectively. Current models may underestimate this concentration, meaning simulations must be updated to match the behavior of halos capable of feeding early giants. Another major revision concerns star formation efficiency. Models often assume that small galaxies in the young universe converted a significant fraction of their gas into stars. But this discovery suggests the opposite, that much of the gas may have gone into feeding the central black hole instead. If true, early galaxies may have been darker, more compact, and more black hole dominated than previously believed. Finally, the discovery hints at the possibility that early galaxies formed more quickly than expected. If early structures assembled at accelerated rates, they could have created environments capable of supporting massive black holes even before galaxies reached maturity. This would reshape the entire narrative of early cosmic evolution. In short, Cannock's LRDZ 8.6 does not merely challenge a single model. It requires a broad re-evaluation of how structure formed in the universe's first few 100 million years. It shows that the early cosmos was more dynamic, more extreme, and far less predictable than simulations once suggested. JWST has triggered a wave of discoveries of compact red galaxies. By counting them and analyzing their distribution, scientists estimate how common systems like Cannock's LRDZ 8.6 once were. In the years before the James Webb Space Telescope began its observations, astronomers expected to find a few early galaxies, scattered sparsely through the cosmic dawn. The universe was young, structure was only beginning to form, and the first galaxies were believed to be rare and faint. Yet as soon as JWST opened its eye and began peering into deep fields, something unexpected emerged. Instead of a handful of early galaxies, the sky was filled with them. Hundreds of tiny, compact, intensely red objects scattered across regions where previous telescopes saw almost nothing. These galaxies became known as little red dots, a population that appears far more numerous than once imagined. Each of these faint red objects has its own story, but together, they paint a larger picture. When scientists map their numbers across different fields of view, they find that these small, ancient galaxies are not exotic outliers. They are representative of a broad population that once dominated the early universe. By counting how many appear per square arc minute and comparing data between multiple JWST surveys, astronomers can estimate their overall abundance billions of years ago. The results suggest that early galaxy formation was far more prolific and efficient than earlier models predicted. This abundance carries important implications. If many of these tiny red galaxies host black holes as large as the one found in Canux LRDZ 8.6, then early black hole growth may have been widespread rather than exceptional. The idea that supermassive black holes existed only in rare early giants becomes less likely. Instead, it suggests that the early universe may have been dotted with compact galaxies that formed black holes rapidly, each contributing radiation and energy to the young cosmos. Understanding how many such galaxies existed also helps refine models of the cosmic web. Early galaxies formed along filaments of dark matter where gas could pool and collapse. The presence of so many compact systems implies that these filaments were rich with material, feeding a vast number of small halos simultaneously. This broad distribution of halos is consistent with simulations that predict a rapid rise in small-scale structure. But JWST's observations push the numbers even higher. It forces scientists to consider whether early matter clumping was even more efficient than previously assumed. Furthermore, by studying how these galaxies are grouped, astronomers learn about the density of the early universe. Galaxies that cluster together suggest regions of deeper gravitational wells, possibly hinting at early protoclusters, forming long before large galaxy clusters existed. If Canux LRD Z 8.6 is part of one such dense pocket, it might help explain why its black hole grew so quickly. Dense environments provide more fuel, more interactions, and more opportunities for dramatic evolution. The collective population of compact red galaxies becomes a statistical probe of the universe's formative years. Their numbers tell us how quickly structure assembled. Their brightness reveals how actively stars formed. Their distribution traces the framework of dark matter that shaped everything. And their diversity hints at many evolutionary pathways, from tiny starbursts to systems dominated by early black holes. In this way, Canux LRDZ 8.6 is not alone. It is one piece of a much larger cosmic puzzle, a representative of a population that once filled the early universe with small, intense, rapidly evolving galaxies. By counting these ancient systems, scientists uncover a hidden era where the cosmos built its first structures in great abundance. Active black holes may have contributed significant radiation during reionization. Studying this galaxy helps determine whether early AGN played a major role in changing the transparency of the universe. Cosmic reionization was one of the most transformative transitions in the history of the universe. After the Big Bang, the cosmos expanded and cooled until hydrogen atoms could form freely. The universe entered a long, dark period where no stars yet existed, and space was filled with cold, neutral gas. Then, with the ignition of the first stars and black holes, intense ultraviolet radiation began stripping electrons from these hydrogen atoms, returning the universe to an ionized state. This process, known as reionization, gradually turned an opaque universe into a transparent one. Yet the exact sources of this radiation have been debated for decades. Were the earlier stars responsible? Or did black holes, in the form of active galactic nuclei, play a much larger role than expected? Canux LRDZ 8.6 enters this discussion as a valuable piece of evidence. Its central black hole appears to have been active at a time when reionization was still underway. Active galactic nuclei, or AGN, are powerful emitters of ultraviolet and X-ray radiation. Even a single AGN can create vast ionized bubbles in the surrounding gas. In a galaxy as compact as this one, the black hole's radiation would have permeated almost the entire system, contributing significantly to local ionization. But the question scientists seek to answer is broader. How many such galaxies existed? and how much cumulative radiation did they release into the cosmos. The spectral signatures from Canucks LRDZ 8.6 reveal highly ionized gas and strong emission lines that are difficult to explain with starlight alone. This suggests that the black hole was actively accreting matter, generating intense radiation capable of escaping the galaxy into intergalactic space. If many early galaxies behaved similarly, then AGN may have been major contributors to the reionization process, working in tandem with early stars to fully ionize the universe. Unlike stars, AGN radiate enormous amounts of energy in a concentrated region. Their high-energy photons can travel long distances before being absorbed, making them efficient at clearing out neutral hydrogen. If early AGN were as common as JWST surveys now suggest, they could collectively produce a diffuse background of ionizing photons across the young cosmos. This radiation would help patch the gaps left by starlight, accelerating the transition from a foggy universe to a clear one. However, black holes also complicate the picture. Their intense winds and outflows can push gas outward, removing the very material needed to produce more radiation. In some environments, AGN may have quenched star formation early, limiting the galaxy's future contributions to reionization. This duality, both creating ionizing radiation and disrupting the fuel supply, makes them challenging to model accurately. Studying Canucks LRDZ 8.6 allows astronomers to quantify this balance. By measuring the black hole's luminosity, the size of its ionized regions, and the escape fraction of high-energy photons, researchers can estimate how much it contributed to the reionization epoch. If its properties are typical of many compact red galaxies, it strengthens the case that early AGN were key players in transforming the universe. In this way, the tiny galaxy offers insight into one of the biggest transitions in cosmic history. It reminds us that the dawn of the universe was shaped not only by the first stars but also by the hidden giants growing quietly in the shadows. This galaxy encourages a new timeline showing black hole growth starting earlier than assumed. This segment examines the big picture timeline rather than the local anomaly. For decades, astrophysicists believed that black holes emerged only after the first massive stars died. The timeline seemed straightforward. Stars formed, lived short and brilliant lives, and then collapsed into black holes that slowly grew over hundreds of millions of years. But discoveries like Canucks LRDZ 8.6 are challenging this sequence. They suggest that black hole growth may have begun far earlier and far more rapidly than anyone predicted. This galaxy is not just an isolated curiosity. It is a data point hinting at a broader shift in our understanding of the early cosmos. Rewriting the timeline begins with acknowledging how young the universe was when this black hole already reached significant mass. Only a few 100 million years had passed since the Big Bang. The universe was still cooling, still assembling its first galaxies, still organizing its matter into the cosmic web. Yet in this chaotic infancy, black holes like the one in Canucks LRDZ 8.6 had already taken shape. Their early presence suggests that black hole formation was not a late-stage byproduct of galaxy evolution. It was woven into the earliest stages of structure formation. This forces scientists to reassess how quickly the first star-forming regions emerged. If black holes were present earlier, it implies that the first massive stars may have formed astonishingly fast. These stars would have lived for only a few million years before collapsing into black holes, offering the earliest seeds. However, such seeds would still be relatively small. To match the masses inferred in some early galaxies, something more is needed. Either black holes accreted material at extraordinary rates, or they formed through more direct channels soon after the universe became transparent. This is where the idea of direct collapse black holes gains traction. Instead of waiting for stars to form and die, some regions may have collapsed directly into black holes under the right conditions. If these processes were common, then black holes could appear almost immediately after the first dense gas clouds assembled. The timeline shifts from black holes forming tens of millions of years after stars to black holes and stars forming nearly side by side. Rewriting the timeline also affects our understanding of galaxy evolution. If black holes were already massive in the earliest galaxies, they would have played active roles in shaping their hosts from the start. These early black holes would have influenced gas flow, star formation rates, and even the chemical evolution of their galaxies. Instead of galaxies nurturing black holes, the relationship may have been reversed in many early systems. As such, the timeline for black hole growth must be aligned with the timeline for the universe's first major transformations, including the rise of turbulence, the enrichment of gas, and the onset of cosmic reionization. On the cosmic scale, these early black holes could have contributed to the background radiation that helped reionize the universe. Their growth histories may be intertwined with the clearing of the cosmic fog. This implies that black hole activity was not merely a later phenomenon, but a fundamental part of the universe's earliest epochs. In reconstructing the big picture timeline, Cannock's LRDZ 8.6 becomes a crucial clue. It suggests that black hole growth began earlier, proceeded faster, and influenced more of the early universe than previously believed. The timeline, once linear and calm, now appears far more dynamic, with black holes emerging as key players from the very beginning. Upcoming telescopes like Roman, ELT, and SKA will examine early galaxies with higher precision. Their findings may explain the origin of early supermassive black holes. In many ways, galaxies like Cannock's LRDZ 8.6 represent the limits of our current observational reach. Even with the James Webb Space Telescope, one of the most sensitive instruments humanity has ever placed in space, the faint, ancient signals from the earliest cosmic epochs hover at the edge of detectability. JWST has shown us what is possible, but it has also revealed how much more we need to see. To understand the origin of early supermassive black holes, and to finally answer the questions raised by systems like this one, the next generation of telescopes will be essential. One of the most promising instruments on the horizon is the Nancy Grace Roman Space Telescope, designed to survey wide swaths of the sky with deep infrared sensitivity. Roman will find thousands upon thousands of early galaxies, giving us the statistical weight that JWST's narrow but deep fields cannot provide. Roman's extraordinary field of view will reveal whether compact red galaxies like Cannock's LRDZ 8.6 are rare anomalies or one example of a vast hidden population. By measuring their brightness, distribution, and redshifts on an unprecedented scale, Roman will provide a broader context that JWST alone cannot supply. Complementing Roman's wide-field vision is the Extremely Large Telescope, or ELT, currently under construction in Chile. The ELT will possess a mirror nearly 40 meters across, allowing it to collect more light than any optical telescope in history. Its adaptive optics systems will sharpen images to a clarity approaching that of space-based instruments, but with the added benefit of greater light-gathering power. For galaxies at extreme distances, the ELT will perform high-resolution spectroscopy that surpasses even JWST in detail. This means it will be able to measure the movements of gas inside early galaxies with extraordinary precision, revealing whether they're black holes formed through direct collapse, rapid accretion, or some still unknown mechanism. Then there is the Square Kilometre Array, or SKA, a massive radio observatory that will span continents. While optical and infrared telescopes study starlight and heated gas, SKA will examine the cold hydrogen that filled the early universe. By mapping this hydrogen across vast cosmic volumes, SKA will show how the first galaxies affected their surroundings. It will measure how early black holes carved out bubbles of ionized gas, and how those bubbles grew and merged during cosmic reionization. In essence, SKA will reveal the fingerprints that early AGN left on the cosmic landscape. Together, these instruments will provide a multi-wavelength view of the early universe. Roman identifying candidates, JWST and ELT studying their internal structures, and SKA tracing their influence on the cosmic medium. Each telescope fills a gap in our understanding, and together they create a roadmap for solving the mystery of early black hole formation. The discoveries they bring may rewrite the story once again. They may confirm that early black holes formed through direct collapse, or they may uncover new processes that challenge our theories. They may reveal that galaxies like Cannock's LRDZ 8.6 were common, or that something unique shaped its evolution. What is certain is that the earliest chapters of cosmic history are only beginning to unfold, and the tools to read them more clearly are rapidly approaching. The distant object offers a bridge between its ancient world and our own. It shows how early structures eventually led to galaxies like the Milky Way, to stars like our Sun, and finally to beings capable of wondering where they came from. Cannock's LRD Z 8.6 allows us to look back at a time when the universe was still learning how to build. Long before spiral galaxies unfurled their arms, or clusters gathered into massive cosmic cities, tiny systems like this one laid the foundation for everything that came after. They were the universe's first attempts at organization, small pockets where matter began to gather, ignite. In the compact light of this early galaxy, we see the beginnings of the processes that would ultimately create the conditions for stars, planets, and eventually life. What makes this ancient system so meaningful is not just its age, but what it represents. Within its tight core, the first heavy elements were forged, released into space by the earliest stellar explosions. These elements would later enrich the gas clouds that formed larger galaxies. The path from these primitive stars to the Sun, and from their debris to the atoms in our own bodies, is a continuous thread stretching across billions of years. This galaxy gives us a glimpse of where that thread began. The presence of a rapidly growing black hole in such a small system reminds us that complexity arose far earlier than expected. Black holes, once thought to be late arrivals, were already influencing the flow of matter, shaping the structure of galaxies, and contributing energy to the young universe. Their early activity helped sculpt the cosmic web and guide material into the places where new stars would form. They were formative forces long before the first mature galaxies appeared. By studying the chemical signatures, the turbulent motions, and the compact structure of this galaxy, astronomers uncover the earliest steps in a long evolutionary chain. These first galaxies merged, grew, and evolved into the larger systems we see today. Over billions of years, small clusters became grand spirals. Primeval stars seeded the cosmos with metals, and the universe that began as a dark expanse of hydrogen gradually transformed into a place capable of hosting life. Cannock's LRD Z 8.6 is a quiet reminder that our story did not begin on Earth. It began in the first sparks of light, in the earliest gravitational bonds, in small, determined galaxies, struggling to form stars in a chaotic young universe. By observing this distant system, we are not simply looking outward. We are looking back at the origins of everything we are. As we drift back from the distant edges of the universe, it becomes clear how much a single tiny galaxy can reveal. Cannock's LRD Z 8.6, no larger than some of the star clusters in our own Milky Way, has carried us through a story that began more than 13 billion years ago. A story written in faint light, stretched by time, and delivered across cosmic darkness so that we could uncover the earliest chapters of existence. Inside its compact shape, we found turbulent gas, newborn stars, ancient elements, and a black hole growing faster than our theories ever expected. Every detail was a reminder that the universe began in chaos and creativity, shaping the structures that would one day become galaxies, planets, and life. When we look into this galaxy, we are seeing more than history. We are seeing the long chain of events that made our world possible. The first stars forged the elements we are made of. The first galaxies gathered the matter that would later form the Milky Way. And the first black holes helped sculpt the cosmic web that guided gas and light into the places where future stars would ignite. In a very real sense, by studying this tiny ancient system, we are studying the beginning of our own story. So, as you settle into rest, let your mind float gently through that vast cosmic landscape. Remember that you are connected to the universe in every way that matters. Your atoms were forged in ancient stars. Your world grew from clouds shaped by cosmic gravity. And your thoughts, at this very moment, are the latest chapter in a story that began long before Earth existed. Thank you for joining this journey across time. Sleep well, and may the stars keep you company tonight.